section 3.5, derivatives of trigonometric functions, page 6. Looking at an example of this simple harmonic motion, we have a weight hanging from a spring and it is stretched 4 units beyond its rest position and released at time equals 0 to bob up and down. Its position at any time is given by s equals 4 cosine t. I want you to find the velocity, the acceleration, and the jerk functions. So basically, we have this spring that we had on page 5, and here it's kind of at rest. Actually, we're going to start here. It's at rest. We pull it down, and we let it go, and it's going to come pull down to its maximum distance, and then it's going to go back past that spot, and then the next one, it would rise back up, and then bounce back down, rise back up. I think you've all played with slinkies before and had the spring bounce up and down. Find the velocity, acceleration, and jerk. So first thing, let's find velocity. Velocity is going to be the derivative of this position. So here's the position function. And when we do that velocity here, bring the 4 down, and then times the derivative of cosine, which is negative sine. That'll give us a negative 4 sine t. Acceleration will be the derivative of velocity. So the negative 4 would come down, and then the derivative of sine is cosine. We have negative 4 cosine t. And the jerk function, derivative of acceleration, so negative 4, but then the sine of the derivative of cosine is negative sine, so that would give us a positive 4 sine t. All right, now I want you to describe the motion of the weight in relationship to position, velocity, and acceleration. And in order to do that, we are going to have to graph each function over a length of 1 period. Okay, the functions that we're interested in, position, velocity, and acceleration. All right, remember back to your pre-calc. How do you find period? Period for a sine or cosine curve is 2 pi over the absolute value of b. And do you remember? That was the A part that told you about amplitude. And the b is the coefficient of the variable here. So for all of these, the period is 2 pi over 1, or 2 pi. What that tells us then is when we graph these guys down here, position, velocity, and acceleration, we need to graph these over a period of 2 pi. The position function here is 4 cosine t. Velocity is negative 4 sine t. And acceleration is negative 4. Oh, did I goof this up? I certainly did. S is 4 cosine t. That's correct. Velocity is a negative 4 sine t. That's right. And acceleration, negative 4 cosine t. Sorry, I thought I goofed it up, but I didn't. All right, we're going to graph these. And remember up here, this number, this A value, oops, can't see it. That A value tells you amplitude. So I know that the height of each of these is 4 and negative 4. And a cosine curve started up normally at a height of 1. This time we're going to start at a height of 4. And cosine at pi over 2 pi over 2 back at 0, 2 pi back at 4. I have to turn the paper to sketch this in. If you've forgotten how to graph these trig functions, Google it, look back at your old notes, go to Khan Academy. Somehow, some way, if I'm going too fast to sketch these, you need to pick those up again. All right, a negative 4 sine t. Sine starts at the origin, has zeros in the beginning and the end. We have normally sine would go up. We have a negative here, so we're going to go down first. And then the negative 4 cosine t, it's going to look just like that position function, but opposite direction. So we're going to start right down here. And we have those curves. All right, now let's go back and let's kind of go through and examine each of these curves and see about what they tell you. This one right here, this 4, that's telling you its maximum length of the spring, if you will. So this is the maximum stretch. This one is the minimum length of the spring, so that's going to be when it's compressed the most. And these spots is you're at that rest position. Also called the equilibrium. So looking at this in here, that's when the spring is stretching. And when we're underneath the x-axis for position, that's when the spring is getting shorter, so it is being compressed. And we see when we look at this a maximum stretch at 0 and 2 pi. We see a maximum compression at t equals pi, and this spring and weight are at rest at pi over 2 and 3 pi over 2. Okay? All right, now let's come down here and let's look at the velocity. Right here at the beginning, before we pull on that spring and that weight at all, velocity is 0. Or before we let it go, actually. Velocity 0, here as well, and here. Okay. Think about where that is. What are those velocities doing? So at time 0, maximum stretch. So we pulled the weight down and we haven't let it go yet. Right here, the next time velocity was 0 when we're at maximum compression. So that spring has gone all the way as tight as it's going to go. And just before it stretches back out again, it pauses for a minute. So that makes sense that velocity is 0. And same thing down here at this 2 pi, All right, other things going on right here at these zeros, we have a change in direction. And if you think about that with the spring itself changing from maximum compression when it's the tightest until when it starts stretching out, that's you're changing the direction. Also, we can see that here with a velocity equal to 0 and a change in sign of velocity. So velocity is changing from a negative value down here to a positive value up here. Okay, all right, and a couple other things. In this section right in here, so all of this bit in here, velocity is greater than 0. So the spring is stretching. Which means that the weight is moving down. And in this section down here, this velocity is less than 0, so the spring is compressing and the weight is moving up. Okay? Notice when we're at equilibrium, velocity is the greatest or least actually, largest absolute value, largest speed, here and here at equilibrium. These spots right here those are your equilibrium spots. So that's in that middle spot when it's just starting to go up, or when it's at middle spot and just starting to go down. Okay, a couple more things I want to look at off of this velocity graph. I want to look at where speed is increasing. Speed is increasing if velocity and acceleration have the same sign. So velocity greater than 0, acceleration greater than 0, or velocity less than 0 and acceleration less than 0. So if we investigate this, where is velocity greater than 0? This is the velocity curve. Velocity is greater than 0 right in here. Positive y values, which is velocity here. And then acceleration greater than 0. Acceleration is slope of a velocity curve. Acceleration is slope of a velocity curve. So in this section in here, where is the slope positive? That would be from pi to 3 pi over 2. So this one is pi up to 3 pi over 2. And where's velocity less than 0? That's this section over here. And acceleration less than 0. It's a negative slope on velocity. That's this bit right here. That's 0 to pi over 2. So these two pieces are where speed increases. Speed decreases when velocity and acceleration are opposite signs. So velocity greater than 0 and acceleration less than 0. Or velocity less than 0, acceleration greater than 0. And again, looking on here, where's velocity less than 0? That's this bit right in here. And where acceleration is, oops, did I say velocity? I better do this one. Velocity less than 0, that's this bit over here. And we want acceleration positive, that's a positive slope. That's pi over 2 up to pi. And velocity greater than 0, that's this bit over here, with a negative acceleration or a negative slope, that's going to be 3 pi over 2 up to 2 pi. It is the two of those. Realistically, I should probably have them in the reverse order so that it would be in numerical order. All right, last bit down here, looking at acceleration. Down here on this one, when acceleration is negative, velocity is decreasing. Acceleration is negative, so velocity is decreasing. Also over here, velocity is negative, so, acceleration is negative, so velocity is decreasing. And up here, acceleration is positive, so velocity is increasing. Okay? All right. We're going to kind of put this all in a nutshell on the very next page.